So now let's wrap up chapter 3, and this actually wraps up everything in the semester through spring break. We have analyzed entirely the problem AX equals B. In chapter 1, we learned the mechanics of solving this problem and found that it was best done, or computationally most efficiently done, with the LU factorization. And we also saw, when doing this, that the solution does not always exist and it is not always unique. And so we saw that there is a particular solution plus anything in the null space is a solution. And we looked at what that means, spaces, in chapter 2. And so we also then saw that if the null space is 0, then the solution would be unique. All the non-uniqueness is in this part as we decompose X. In chapter 3, we saw this decomposition of B. We know that the existence of a solution depends on B, and in particular, it depends on this column component. B decomposes into something from the column space, but then also this error component, which from the projection theorem is in the left null space of A, meaning that it's orthogonal to that column space. And in order for the solution to exist, we would need this part to be 0. So our fundamental theorem of linear algebra is very theoretical, but it has practical implications on this problem. So this problem does not always have a solution, but we did find that even when this solution doesn't exist, we could get a least squares solution, or a solution to the least squares problem. The fundamental theorem of linear algebra says that for a square matrix A, the row rank equals the column rank, which means that if the row rank is full, meaning that the null space is 0 and the solution is unique, we also know that the solution will exist because the column rank will be full, meaning that the left null space will be 0 and that there is no error. Now that B is entirely in the column space for any B. So the fundamental theorem of linear algebra tells us that the row rank equals the column rank for square matrices, and it also tells us that the row space is orthogonal to this null space. And then also the column space is orthogonal to the left null space. That has a projection flavor to it. So that's what we've gotten in the first 3 chapters. Come back after spring break. I can't wait to see you guys again. And we will get into the matrix analysis portion of the course. So that some of the theoretical stuff is completed now.